Let's explore today's supporting code. You can find these files in the Lecture 20 Parser directory of lecture, and I'm looking at the files in the include directory that give us the header files of our project. So let's start from the most basic that we've seen before. Guards.h, of course, is where we've declared the guard for out-of-memory error support. We looked previously at a char iterator concept, and we'll briefly look at that today. Our token.h file contains the declarations for our tokens and the token types, so we're going to take a look at that. Scanner is going to be the abstraction that takes in a char iterator and produces a stream of tokens that are peekable. And we looked at how we can define a node struct as well as the enum for the node value and for the node type, and then the union for the node value. And so what we moved through in the previous video is going to be very similar to what we see in node.h. And lastly, the parser.h file is going to have our parse functions that implement our grammar, and that's where we'll be spending our time primarily. But before we get there, just to try and familiarize you with a few of the abstractions we're using here, let's start with the char iterator implementation. So if I open include char iter, notice that we are going to be able to iterate, create a char iterator value by giving a pointer to the start of some array of characters and a length that will determine how many characters can we iterate through given this iterator. So this is slightly different and slightly more involved than the char iterator we saw before, where we just used a single pointer and went until we saw the end of a string. This would allow us to write or to set up a char iterator value if we wanted one that only went through partway through a string, some specific length, and then stopped after that. Right? Just like before, we can get a cursor or a pointer to that char iterator. We can ask the char iterator whether it has any additional content to be consumed in it. That will be true until we reach the end, or we've taken the number of length characters from it. We can peek ahead one character, and we can ask it for its next character. Right? So nothing too mind-blowing there. If we then turn our attention to the token file, this is where we are defining the types of tokens we have. So the enum token type. We have an end token. This would be when we reach the end of a line or a stream, end of file. Just a generic ending token. We have a char token. This will be anything that's not a space, an L-paren, or an R-paren. And then we, of course, have token types for those as well. When we define our token struct, notice we have a token type, which is going to be the enum, and then we have a single character lexeme. And I added this comment because when we write a parser for a shell, this won't be the lexeme won't be a single character for a token, right? That's something that's special to the char pair grammar that's simplified so that we're not really focused on the scanning and tokenization of our input. We've got very simple tokens here in lexemes, but normally this would be a slice. So this would be some subset of characters out of a larger string, right? So this will be something that when we get to implementing our own parser will be different. And you'll need to think a little bit harder about. But for now, each token is a single character, and it keeps track of its lexeme. So if I were to look in the scanner header file, scanner is going to feel a lot like an iterator, right? So in fact, it is an iterator. We think of a scanner as an iterator. It's made up of a character iterator, and then it's keeping track of what is the next character that I will iterate over so that we can achieve peaking and peakability. In a real scanner, this would actually be a full-fledged token. So there will be some work for you to do when we go to write a real scanner for a shell grammar. But for now, again, all we need to focus on is what is the next character. So that's what we're storing as part of the scanner's internal state. And just like the character iterator, a scanner, we can peek, we can ask it for its next value, we can test whether or not it has another value, right? So whereas a character iterator is producing one character at a time, a scanner, notice, is producing tokens at a time. And so it's built in terms of a character iterator, but it's giving us a higher order abstraction to be thinking about at the token level. Okay? And if I were to then peek in the node.h class, This will look very similar to what we defined in the previous video. We've got our node's type, but I've added one additional kind of node, an error node. And we've got our pair value, our char value, and then the error value is another type of value, right? And so this is a character pointer. So this would be pointing to the start of a C string that describes what is the error that we encounter. And our node value then can be any one of these three types of values. And this is defined in a union, right? And so then each node is going to have a type and a value in its data field. And then this header file is setting up some helper constructors effectively for allocating some memory on the heap and returning a pointer to a new char node, a new pair node, or a new error node. And we think of these as constructors that we can give arguments to in order to initialize the fields of that particular node. And to each constructor will be responsible for setting the type member of that node value. And we can go take a look at that in just a moment. And then lastly, because we are allocating heap memory for each of these, we're implementing a drop function that will need to free up any memory that was allocated in the construction of these nodes on the heap. All right. Lastly, we have our parser.h, and this one is very straightforward, right? So this is only surfacing a single top-level function. The other functions will be private to the parser file itself, and we'll be focused on that next. But notice that the parse function takes in a scanner. So remember, a scanner is going to produce a stream of tokens that we can peek ahead by one with. And it's going to return to us a pointer to a node on the heap that's going to be the result of the parsing process. It will be effectively the root node of our parse tree that we get back a reference to. The last thing I want to point out before we jump into thinking about setting up the parser is looking at the node.c file in the source directory. So I just wanted to point out these constructors. Notice we are setting up a node pointer and we're mallocing the size of a single node. And then each of these constructors is doing the work of setting the type of node that we're constructing, right? So the type of a char node is char node, and setting that union member, the data member, to be whatever we're initializing the data of a node to be. So with the error node, we can see that its type is error node, and that union for a node value has an error value that we access through the .error selector. With the pair node, its type is pair node, and then we have the left and the right fields of that pair struct that we can assign those pointers to. If we take a peep into the main function, we'll see that just like in the previous lecture where we were having a statically allocated line length size, or the maximum line length here is 1024 characters, and we've got a very naive implementation of reading a next line into some buffer. In our main program, we've got something pretty simple set up. We are reading a new line into that buffer. We are setting up an iterator that begins at the start of that buffer, and it has a length of the strlen, or the length of the buffer itself, not including the null character. And we are then setting up our scanner. And so the scanner will produce tokens. And the scanner's input, what a scanner is based on, is a character iterator, right? So we're giving the character iterator to the scanner. And then we've imported that parse function from the parser.c file, and parse takes the scanner and we'll use it to produce a sequence of tokens that it is then going to turn into a parse tree. And it will return to us the root node of that parse tree. We are going to come back to, and in the next video, we're going to talk through what is this visit function. We're going to visit each node of our tree to print some output relative to each node. And this 0 is how much indentation do we want to have, how many spaces before each line of output. And we'll increase that recursively so that we have indentation on each output line. And then lastly, we need to be sure that because we parsed an output tree here, we need to drop that output tree and be sure that its memory gets freed before we continue on. Right? So this is the main function, and we'll come back and look and work on the implementation of this visit function after we implement parsing. Okay, so let's work on implementing this parser together. What we're going to do is open up the source parser.c file. And there's some scaffolding code in here, including some comments that describe the grammar, right? So our grammar is a node is made up of a char node or a pair node. Char node is made up of a char token, pair node of a left paren token, a node, which is our recursive rule, a space token, another node, and then an r paren token, right? I've gone ahead and declared these three functions that we're going to need. Remember, part of the process of implementing a recursive descent parser is take your production rules and make one function for each of them. So this parse function, which the header for the declaration of it was in parser.h, this parse function is actually our top level rule, right? This is our starting symbol node. And so parse is going to return a node. The next two rules, their function definitions are down below the parse function, but because the parse function needs to be able to call them, I've gone ahead and declared them ahead of time. So notice we've got this parse pair that would correspond to the pair node rule, and this parse char function, which will correspond to the char node rule. So that first step of define your functions that correspond to your production rules, we've gone ahead and taken care of. So here's the top level rule, and then here are the two production rules that we'll need to go and implement next. Right? But before we get there, let's take a look at some of what we set up in the parse function on your behalf, right? So parse is given a scanner, and remember the scanner has functions like peek related to it. We can peek the next token. And here, because we have alternation in our grammar, we don't know whether or not we need to go call char node or pair node. So what we need to do is peek one ahead and look at, well, how can we tell which one of those two functions we're going to call? Well, if we know that the next thing that we would expect in char node is a char token, and the next thing that we would expect in a pair node is an L paren token. So what we do is we peek that next token, and then we switch we create a switch statement based on what type it is, right? So we're saying, what is the type of the next token? And in the case where that's a char token, we're going to call the parse char function and give it the scanner. And that is going to implement the production rule for parsing a char node. And if it's an L paren token, right? If we looked ahead and we peeked and we saw that there's a left parenthesis, then we should begin parsing a pair, because that's the only other thing it could be based on our grammar. It's going to be a pair node that we return. If it's neither of those two things, what we're going to do is we're going to return an error node. And we saw the error node constructor before. Basically, this will be a node that can give us a little bit of helpful input to say, hey, we expected there to be either an open left parenthesis or some character here. All right. So let's consider how is it that we would actually implement, say, this function of parse a character, right? So I'm going to delete my return statement here, and what we first need to do is get the next token, right? And so we can do that with the scanner next function. And scanner is already a pointer to a function, which is, the scanner variable name is already a pointer to a scanner struct value. So we can use that directly. We can pass it in directly. We don't need the address of it. And what this token is going to be, we know that we got to this place, like we as the implementers of this function, we know that we got here by virtue of the parse function seeing that there was a char token, right? So we know that we already have a char token. If we wanted to be doubly sure, we could add another if statement here and check it and be sure. But we know that there's a char token to be had here. So we're going to trust that. And what we're going to do is we're going to return a char node value. Right? And actually the constructor here is new. This is a new char node. So this function is a constructor function that was defined in the char.h, the node.h header file that we looked at previously. And this constructor takes a single argument, which is the character that we want to have stored in that character's data property, right? So if I were to split my pane here and open up include node.h and scroll down to where we see the definition of these constructors. Again, what we're trying to construct here is a new char node, and its constructor parameter is just what is the char value stored in this node, right? And coming up, we'll see previously we looked at error node and we gave it a pointer to a C string constant, which we saw here. And in parse pair, we're going to make use of this constructor. So I'm going to close this pane, but keep it in mind that we are going to need to call pair node underscore new to construct a new node object whose type is a pair, and we're going to give it the left and right pointers of those two values, right? So we are now going to try and implement recursive descent parsing for this parse pair function. And this is where things get more interesting, right? We have 5 things that we need to do in order to implement this production rule. The good news is we can follow them pretty directly, right? I'm going to approach this first in a very naive and trusting fashion, in the sense that we're going to trust that the user input is correct and we're not going to worry about errors right off the bat, right? So what's the first thing we need to do? Well, we got here by virtue of peeking and seeing that there was a left paren to start us off, right? And that's what led to the call parse pair and got us here, right? So we know that the first token, and I'm just going to set up a local variable named next, and we're going to use this a few times. And actually, this is a token, not a node. So the next token is going to be initialized to be, and I can go ahead and initialize it here, the next token from the scanner, right? We know by virtue of how we got to this point that this is going to be a token whose type is L_paren. We don't actually care about that L_paren, right? That's just syntactical sugar that allows us to know we're working with a pair in our grammar, right? So what are we going to do after this? Well, the next thing that we want to do is get this node recursively, right? We want to parse whatever comes next, this next node recursively. So I'm going to set up a node pointer for the left node, and it's going to be the result of calling the parse function with the scanner, right? So remember, this is what recursive descent is all about. And I can't fit both of these functions on my screen at the same time, but this parse rule is the one that implements the production rule in our grammar that parses a node that can either be a char node or a pair node. And what we're saying here in the parse pair function is the pointer to the left node is the result of calling parse with scanner after we just took that left parenthesis, right? So the left parenthesis was consumed. And now whatever comes next is either going to be a pair or a char, but it's going to be up to the parse function that returns a node to decide which direction to take that in. And this is what we call mutual recursion, right? There is, if we had nested pairs in our input string, pair would wind up calling parse, and then it would wind up calling parse pair again, which would then call parse again, and there would be mutual recursion going on there. And this is why this is called recursive descent, right? So the next thing that we would do is take the next token off of the scanner, right? And so this is going to consume the space token. Now, we would probably want to be sure that that actually was a space and be very careful to handle cases where that wasn't spaces. But again, we're going to leave error checking and error handling out of this example for the purposes of illustration. So we just consume that space token, and maybe I'll make a note of it. All right. And then we're going to want to parse the right node of this pair of values. So the right node is another node pointer that is the result of calling parse again with our scanner, right? And notice what we're doing in passing around this scanner is as these parse functions are evaluated, we're taking the next token from the stream of input tokens and moving the scanner forward, right? This is what's progressing us through processing our input. The next thing we're going to need to do is say next is the next token from the scanner. And again, we're trusting the user to use this language properly, and we're consuming the r_paren token, right? Once again, on trust. All right, so now we've taken this entire rule, right? We've got 5 steps here. We are consuming the left paren, and then we're letting recursive descent handle the parsing of this node, which is now going to be stored in our variable named left. Same with space, followed by another node and r_paren. So now what we have left to do is we need to return and we looked at this constructor previously, a new pair node, right? And that pair node constructor had 2 arguments that we needed to give it to its parameters, left and right. Right? And so Notice there's a one-to-one correspondence with how this grammar rule was specified and the implementation of our recursive descent code in C. Right? It wasn't quite as clean as that pseudocode, but it's not too bad. I will note that this, as you add error detection, this will get a little bit uglier, right? There are more checks we needed to do. We should have checked to be sure that what came after this node was a space. Like that's what our grammar says is expected there. We should have checked that there and made an error, surface an error if it wasn't one. Same with declosing right paren, right? But we're doing those things on trust for now, and we're gonna call that good enough, right? So this makes up the basis of a recursive descent parser. And hopefully you're getting a feel for the relationship between the grammar and the code that is going to effectively implement the parsing of that grammar. Next, we're going to turn our attention to the visit function in the main program to print some output based on this scanned structure, this parsed structure that we've derived from our input string.